Okay, welcome to 240. Well, first of all, that midterm, let's do it on the Thursday, the 18th of March. So let's decide for that day. That will give you one more office hour to ask questions. Also, homework number 2 is back, so pick it up, please, at the end of class. We've started talking about OTAs. And we've talked about the differences or comparison of OTAs with the sort of more familiar operation amplifier. And the difference really is an OTA has a current source at the output, and so its gain fundamentally is a transconductance, and it's got a unit, right? And an operation amplifier has a voltage source at the output, and because we drive it also with a voltage, it really is its gain is a voltage gain, and right, is unitless. And when we looked at some of the differences and the implications, and so one of the big things, of course, is that with an OTA we really can't drive a resistor because the achievable voltage gain depends on the load, and for sort of practical values of resistors that we can build on an IC, that would be fairly poor, and we couldn't get reasonable gain except if we made these transconductors horrendous. On the other hand, there are some advantages, of course, the obvious ones, like we don't need extra elements to provide low output impedance, and especially at low voltage, those are very hard to design. We'll look a little bit at buffers. Sometimes, of course, they're needed. If you want to drive an Ethernet cable here, well, you better put the buffer here. It's probably not going to work with just a transconductor. And then one of the differences also was noise, because basically we have a simpler system here. We also get less noise. And also hidden in this very simple picture is the rather profound and interesting observation that cation C noise and the noise from the operation amplifier, they do not somehow add up or so. They're one and the same. There is no distinction between them, right? And that, of course, is very helpful. So somewhat simplifies design and analysis, but also it precludes us from guessing possibly wrong noises. I also had made here sort of a model of an operation amplifier and analyzed its noise and got more noise. And then I got some input from some of you that this is really a little bit of a too simplified picture. It's not always quite adequate for an operation amplifier, because really generally the bandwidth of an operation amplifier is not given by the load capacitance, but it is given by capacitance either hanging at this node or by a compensation capacitor inside. And we'll see that later when we analyze two-stage amplifiers. Then that in that case the noise also is not cation CL, this C, but cation whatever capacitor actually determines the bandwidth of the system. So and in that case, sort of the comparison is not so obvious anymore because we have different C's here and so on. But generally, because we have more components here, there is hardly a noise advantage building a operation amplifier. And now I'm on. So anyways, I think you will, despite sort of the perhaps initial unfamiliarity, I can't even use a resistive feedback network, it probably will not take you a long time to embrace the idea of using OTAs, and you will not try to build op-amps on your chips to build your A to D converters or whatnot. Okay, so now there is, of course, the problem. Well, heck, if we can't use resistor, what are we going to use as the feedback network? So And of course, we still need feedback because otherwise we really can't generate a precise gain over a sort of large input range, linear and so on. So, well, if actually, so now, in fact, when I'm not absent-minded, then I actually draw this symbol here for a transconductor and this for an op-amp. Idea being that this triangle here is the buffer, the 1x buffer that isn't present in the transconductance amplifier. So then also, usually I'm too lazy to draw this extra terminal here. I just do it here once, right? So let's try capacitive feedback. So usually I call this CS and this CF. And this would then be V in and here V out. Well, current flows in here and flows through the feedback capacitor. The operation, the transconductance amplifier, provided this feedback loop is stable, will keep this voltage a virtual ground node, and consequently VI really appears across here, and the voltage that appears across here is V out, so V out is then equal to minus VI times CS over CF. It's really exactly the same thing if there had been resistors, then V out would be equal to minus VI times RF over RS. Notice that, of course, it's inverted because in one case we have admittances and the other one impedances. Okay. So the problem with this circuit, of course, is that we need to somehow bias this node. Otherwise, the capacitance could be charged to any arbitrary value. For example, a very large value, and there would be just no way for ever getting a virtual ground node here. So in practice, we need some kind of circuitry to initialize these capacitors. There are lots of schemes that come to mind. For example, we could like we've done in the homework, put the humongous resistor, let's say, to ground here or to some other appropriate bias. But in practice, that had several problems. One, the obvious one, that heck, how are you going to build this humongous resistor, right? That would take the entire chip in terms of area. And the other one is that then, of course, the characteristic from here to the output would no longer be a constant gain that ultimately rolls off when this thing loses steam, but it would have a zero at low frequency, depending on how big we make this resistor. So it really would not be a DC amplifier anymore. Right? It would be AC coupled. So that's another practical problem. So what really works and what is used in practice is that we use switches to temporarily short circuit these capacitors, something like, to put the right voltage across them. That introduces that sort of introduces the notion that sometimes our circuit is unusable because we are, let's say, deleting the charge stored on CF, right? And one way to deal with that would be to sort of do that only, let's say, when the circuit is powered up or something like that. Practice, such schemes don't work very well. Turns out that because of leakage and so on, charges, undesired charges, regularly accumulate on these capacitors. So we will need to do this at least, let's say, every second, or maybe even a little bit more often than that. And then if we do something like that every second, then every second our signal has some artifact. So in order to avoid these troubles, actual implementations, they use a clock, let's say the clock rate of the A to D converter that is used, that this amplifier is used in, and they just do this reset on every clock. That way you don't have an artifact that occurs in some clock cycles, but not on others. Okay? So how do we do that? Well, there are plenty of different circuits to actually do that, plenty of implementation. I'll just show you one to convince you. Well, I mean, it's a little bit unusual perhaps, but it's really not a big deal. And we certainly can can live with this. So okay, here is the so this circuit now has to run from a clock, and I'll show what the clock is later, but I call it a non-overlapping two-phase clock, and the clock phases are called phase 1 and phase 2. Right? You have like you have in digital circuits. So this would be the capacitor CF, and then regularly during phase 1, we simply discharge this capacitor. So that would be tied to phase 1. Phase 1 on, meaning the switches are closed. Here I just show switches. In reality, of course, we are going to implement those with transistors. Most transistors make pretty good switches, and we'll talk about that later. But for now, we just use these kind of ideal switches. Hey, wait a second. I'm during phase 1, then this switch here is not only discharging CF, but it's also shorting the amplifier output. Is it going to work? Are you going to build this circuit? Short-circuiting the output of... Why is it okay to do that? Yeah. Michele, right? Yeah.
Because it acts like a current source. So
right, exactly. It's a current source. Of course we can short-circuit the current source. We just get the current of the current source coming out. Probably there is a tail. There is a diff pair with a tail current source set to 200 microamps, and the 200 microamps just flow into the output. It's actually good that we short-circuit the output, because otherwise a current source got to spit out its current somewhere, and if it cannot spit it out, then all the levels inside the amplifiers go haywire. So it's actually a very sensible thing to do. Of course, if this was an op-amp, forget it. You will need an extra switch here that opens during phase 1. So that switch would be labeled phi 2. But here, just fine. Right? So then there are several ways on how to connect the capacitor at the input, but one solution that works quite well is as follows. So here we have VI, and then this switch here we also close on phase 1, and this switch we close on phase 1, and this switch here on phase 2, and here also on phase 2. Okay? So now our circuit is complete. Now what we got to do is understand what the heck it does, and for that it's kind of useful to understand that really what we've built is at least 2 and perhaps 3 circuits. We've built the circuit, how it's connected during phase 1. We've built the circuit, how it's connected during phase 2, and we've built the circuit where neither phase 1 or phase 2 are active. In fact, let me draw the clock diagram here. This would be time, and this is sort of closed, and this is open. And this is phase 1. And then we also have phase 2. This is phase 2. And non-overlapping simply means that there is a non-zero delay between phases 1 and 2 where none of the switches are closed. And of course, in practice, you're not going to make this so large here, right? If you think about it, if you build a 100 megasample A to D converter, this entire thing from here to the next phase 1, this thing is 1 over 100 megahertz, so this would be 10 nanoseconds in that case. And so the best you can allocate to these 2 phases, most of the time they're made equal in duration, although sometimes there is good reasons to use other breakdowns, but you got to be careful if you do that. Then for one phase, the best you can do is 5 nanoseconds, and from that you sort of lose what's in the middle. So how much are you going to lose? Well, you're going to slice nanoseconds, right? Few hundred picoseconds. That's what. And then of course it's challenges routing all the clock signals that skew doesn't sort of destroy the non-overlap, right? Okay, so let's now draw this circuit again during phase 1. Incidentally, this circuit is precisely the same one that is also in the notes. I just draw it here again. So during phase 1, all the switches labeled phi 1, they're closed, and so they're short circuits. And all the switches that are labeled phase 2, phi 2, they are open and consequently can be totally ignored. So we have Vi then that connects to a switch that's closed to CS, and CS on the other side also through a switch is connected to ground. The amplifier yeah, it's actually 2. Yeah. I guess I could have drawn this a little bit differently, but that's correct, right? Okay. So CF is short-circuited, means that the charge on it, all the charge on it is dissipated in a switch. That switch gets a little bit warm. Just today I got a paper from somebody who analyzed the problem of the wires in a chip heating up. I wrote a long story on it. What do you think? It's an issue? Apparently not. That's his conclusion, but you can always write 10 pages about it, right? I wouldn't recommend particularly that as a PhD thesis, such a topic. Right? Spent 3 years, but that didn't matter. Okay, so also during phase 1, we're just imprinting the voltage Vi on CS. So the charge, well, because both sides of CF are connected to ground, right? And ground is one terminal, so really, I mean, it's like a short, right? It goes through 2 switches, but then it's shorted. Phi 1. Phi 2 is open, yes. This one's phi 1, yes. Yeah. Okay, so during phase 1, you need some appropriate notation. We are storing on CS a charge that is Vi times CS, right? And the charge on CF during phase 1 is 0, right? Okay. Then you have this Vi times CS, 0, right? For these charges. All right. So then during phase 2 is okay. I'll the next page. We again draw the circuit. Now configuration is pretty much the way we've drawn it first. CS is now connected to the input and shorted to ground on the other side, and CF now appears as AO. Okay, CF as a capacitor across. Okay, so what's going to happen? Well, at first, when we make this connection, CS is still charged, and the voltage, in fact, across this CS is equal to Vi, right? So just when we close the switch, then there is some capacitive division and so on, but at any rate, we are going to see a blip. If Vi was positive, then a blip of the voltage at this terminal here, Vx, is going to drop from 0 down, and so the height of this drop is going to be some factor alpha times Vi height, and alpha really depends on how much capacitance we have there. It's less than 1. It's nothing of amplification. But then the amplifier gets in gear. And why does the amplifier why does this happen? Well, because the amplifier is relatively slow compared to these switches, which instantaneously yank the connections around, right? So, but ultimately the amplifier, of course, if the feedback loop is stable, will restore the virtual ground here. So what has to happen on this Vx is that this has to go back to 0. Well, that means that ultimately this voltage across Cs drops to 0, right? So where does its charge go? Well, it can't flow into this amplifier. It has to flow onto Cf. So all of this charge flows onto Cf. So at the end of phase 2, Qs at the end of phase 2 is equal to 0, and Qf at the end of phase 2 is equal to Qs at the end of phase 1. Right? And now we can easily calculate what the voltage is here at the end of phase 2. So Qs at the end of phase 1 was equal to Cs times Vi, and then Qf is also equal to V out times Cf, and consequently we can solve for V out over Vi is equal to Cs over Cf. Okay. Just as we wanted. The only thing is, this is true only at the end. That's true only at the end of phase 2. And at all other times, it's not correct. Like, for example, with the switching scheme that we are using, during phase 1, the output is shorted, and it's 0, right? Okay. And during phase 2, well, it's going to go more or less slowly, depending on the speed of this amplifier, from 0 to that correct value. Yeah, well, we'll look at the simulation results to see that a little bit better. Yeah, okay, good that you asked. I almost forgot to say that. No, actually not. Because what happens is that we are charging this Cs to the input voltage like this, and then we flip around using the switch arrangement. We flip actually effectively around the capacitor so that now suddenly the other side is grounded and no longer connected to the input. The input now effectively has gone to the other side. So that produces an inversion here, and then the amplifier produces another inversion altogether. It's a positive amplification. So actually that's a very nice sort of side effect of using this switch business. We can build amplifier feedback stages that are single-ended and give us positive gain if we choose, if we like that for some reason. If we want to have a negative gain, no big deal. We just use a slightly different switch arrangement where let's say during phase 2, this one phase 2 and this one phase 1, right? You can draw the configurations yourselves, but what happens in this case is that during phase 1, Cs, just like Cf, is connected to ground and therefore discharged. Now we have a known charge on Cs, 0 happens to be, right? And so now this thing with, oh, we don't know where we are starting from, that problem's gone away. And then during phase 2, this one's closed, this one's closed. We just have an amplifier that amplifies whatever now we put at the input. in practice, when we cascode these, we like to alternate them so that we don't have a whole bunch of the red case all in series, because all the amplifiers, they would have to settle in series, one after the other, right? And that takes extra time. So then having the black case every once in a while is nice because it breaks the chain. So there are lots of opportunities. Actually, sort of, once we start thinking about this, this is not a disadvantage, it's actually an advantage, lots of opportunities. Of course, in some cases, when we really have a continuous time signal and so on, then we got to be careful, because the minute we sample here, we get the aliasing, right? And we have to run this switch fast enough for either an anti-aliasing filter or the like ahead of it. But, those are all valid issues and so on. We got to figure those out, largely a problem of 247, and there are plenty of ways to do that. For now, what we really take back from this is that this is very practical, and what we need really is, what we're going to focus on, is this transconductance amplifier. Okay. So I put this into the computer and ran it through SPICE. Now, if you can just give me this frame. Okay. So I set this so that I would get a gain of 2 just by making CF half as large as CS, right? And so then this smaller sine wave is the input that I actually stuck into my circuit, and then the dashed larger sine wave, that's the output that I would be getting if I had used the continuous time amplifier. Now, because I have this switch capacitor kind of business, of course, I'm not going to get this output. The output is valid only at the end of phase 2, right? So in particular, the end of phase 2 is this point, and then again this point, and, well, I guess this point here, right? Well, now, but here it doesn't actually agree, right? There is a difference between that. That's what comes out here, and that's what our estimated. That's what our ideal amplifier, continuous time amplifier, would produce. So it's not working, right? It's wrong. Here we said that this is at the end of phase 2. You can look on the earlier slide where I mark phases 1 and 2. So this is phase 2. So here we are at the end of phase 2. So that's all fine. But the output of our actual amplifier, that's the green line here. The ideal output is just the input multiplied by 2, and I conveniently put this in this purple line. And we said at the output of phase 2 they coincide. Well, they don't. Something's wrong. What's wrong? Well, the question is, what does our amplifier really amplify? It amplifies the voltage that it samples on CS during phase 1. And particularly the sample that it gets is the value at the end of phase 1, right? That's what it takes. So it actually takes this value, multiplies it by 2, and spits the result out at the end of phase 2. And it matches like a charm. You can do it again here. It grabs the value at the end of phase 1, that's this one, multiplies it by 2, and that's just the right result. One more time. Fetches the value here, multiplies by 2, and lo and behold, matches. Okay? So it's an amplifier by 2, but only at certain time instances, and it's got also some delay built into it. Well, A to D converters anyway sample, and they take their time to do the conversion, so why not the amplifier also? Now we have the next interesting thing to look at, of course. Our favorite topic, right, is noise. A little bit less zoom now again. Our favorite topic is noise. So What's the noise implication of this? Well, the feedback network, all capacitors, right, they ought not to give noise, but now we know better, right? We drive them for something, we have these switches, and altogether we get noise, right? So we get noise from our sampling capacitors, from our feedback capacitors, and then we also, of course, get noise from the amplifier itself. And for that, I'm going to extend my circuit a little bit. That at the end of phase 2, I'm actually sampling the output onto a capacitor CL. Right? Probably this CL is going to be the input capacitance of a next stage. Right? Probably we are just going to cascade blocks like this. Of course, there are going to be a few extra capacitors and switches so that the overall thing does something interesting, like filtering or some computation that gives us A to D conversion or the like. But roughly, it's really essentially what we're doing is we're taking contraptions like this and just cascading them, and so it's reasonable to include that thing here. That just corresponds to this section here. That phi 1 is phi 2 right there. Okay, so what about noise? Well, we better break that up into phase 1 and phase 2 also. Phase 1, well, for that we can go again back to our circuit here. Well, what now happens during phase 1 is, for example, we are clearing the charge on CF. So the charge at the end of phase 1 that's stored on CF ought to be QF equals 0, right? Is it? Is it? What happens if I give you a capacitor? I tell you, go and discharge this capacitor. Can you do that? If you just use a wire and short circuit it and then open it again, what's the voltage that's stored on the capacitor at the end? Yeah, KT on C. So in reality, the V square that's stored on CF is equal to KT on CF, right? And now if you want to know what is the charge, well, then we can do that also. QF squared is equal to VCF squared times the transfer function from voltage to charge. That's the capacitance. And because we are dealing with squares, we get to square this also. So this is equal to KT times CF. Okay. So that's the variance of charge after going through all the effort of actually getting rid of it. In the end, we still have some. And that's the variance of it. And the mean, of course, is 0. Okay. So this charge sample, of course, amounts to a certain voltage. We don't know its value. We know only its variance. And so sometimes we were just lucky and we have 0 volts there, or maybe a femtovolt, right? Something we can't even measure. And sometimes it's going to be a microvolt, and sometimes minus 700 nanovolts, or whatnot, right? Depends on the size of the capacitor and luck. Right? And during phase 2, then, that charge is still there. And it's just going to be added to the signal, and it's going to corrupt the signal. Right? Okay, before we get to that, let's look at CS. Well, CS, of course, is going to collect the charge corresponding to the input signal, VI times CS. But when we open the switch, we also get extra charge. And what's the variance of that charge? The variance of that charge sample, that noise charge sample? It's like my kids, they make an incredible amount of noise. But when I ask them something, I need a big amplifier. So what is it? Same as usual. Okay, I don't remember what is usual. Tell me, what is it? Over there, you can say 2. KT over CS. Are you sure? Why do you say that? Got to be very careful about that. See, in practice, we've said that probably this amplifier here afterwards is loaded by an amplifier like this one and goes on like this, right? So really the situation is something like this. There is a OTA 1 that is driving through switches that are actually closed. Capacitor CS, right? That's what's really happening. So this is OTA 1, and over here is our OTA 2. That's the one we're really talking about now, but somebody is driving this capacitor CS. And in this circuit, what is the noise that I'm getting onto CS? Who has done the homework? Yeah, so then you know the answer, right? For example, if we use the OTA problem 1 in the homework, then the noise would be KT on CS times some factor, right? And I'm not going to say this factor now just because otherwise I'll spoil the fun for the rest of you to figure out what that factor is. So there's some factor, and that factor usually will be larger than 1, right? So KT on CS, that's true if we are driving, right? We've analyzed this in this OTA business, right? Really, what we depend on is we have an R out and we have an R noise, right? Actually, including the switch, right? The R noise makes it that the noise is the R noise gives us actually the noise. It's the equivalent noise resistance of the amplifier, right? And the R out makes it that noise is filtered. Well, if they're just equal, then the integral comes out to be just KT on C. But if this one's bigger than this one, well, then we get extra noise. And if the other way around, we actually get less noise. Well, most of the time we get extra noise, like if you do this homework, if you do the homework, you will find that this factor here, forget about 2/3 there, without the 2/3, ignoring the 2/3 there, this factor is always larger or equal than 1. If you have infinitely large supply voltage, then maybe you can make this factor just 1, but not better than that, with the amplifier that you have in the homework. There are other amplifiers, and then the factor is something different again. Right? Okay, so in practice, usually I call this factor here NF. The noise factor of whatever the amplifier, whatever the thing that's driving is, right? And so the noise sample that we get here, the variance of the voltage on CS due to noise is really KT on CS times some factor, NF. Right? Now, it's quite interesting. If you sell an A to D converter, and it's built in CMOS, and that's the most likely choice, right? And then actually the input of the A to D converter is also going to look exactly like this. Now this amplifies none of your problems, right? It's whoever buys the A to D converter has to stick a signal into it. Well, when we design A to D converters, we always spec them for the case where R out equals R noise, and so this factor NF is equal to 1. But if the user goes and uses a practical amplifier, probably that NF is larger than 1, and so he actually gets worse noise performance. But that's his problem. He got to fix his amplifier, right? We say, you build the best possible amplifier. That's NF equals 1. The fact that we don't know how to build that amplifier either, well, our competitor specs support the same way, right? So, okay. So if it's on the chip, however, then we got to be careful. We better include the NF because it's not going to work right otherwise, right? Okay. Questions? All right. So apparently we are going to during phase 1 we are getting two noise samples that are just stored onto these capacitors, right? And they have no other chance but during when the amplifier is really in business, it just pumps that. They're now, once we've opened the switches, then there is nothing random anymore. It is 20 microvolts, right, the noise sample, and that noise sample is going to go over there, and it just sits there. So we don't know ahead of time what it is, but once the switch is open, it's really a deterministic voltage, nothing particularly noisy about. So let's forget for the moment about the noise of the operation amplifier and just figure out what is the variance of the voltage out here based on these noise samples that we captured during phase 1. Right? And that's so during phase 2, there are really two things that happen. First, we are taking the voltage, the noise sample that was stored, what was loaded onto CF during phase 1, and that just appears at the output, right? And then we are also taking this other noise sample, KT, on CS, that may have this nasty NF in it. But that one doesn't just add to the output, it is amplified. It is amplified by the exact same gain as the input signal, as all the other charge that we've stored onto CS. So, and again, don't forget the square. Okay. So that's the feedback network. Okay, so that's our first noise. Now we use the fact that that we have linear superposition. So during phase 2, now the amplifier also puts out its own, generates a signal and charges CL to the signal, but it also puts out its own noise that, together with its output impedance and the switch resistance and CL, is low-pass filtered and produces a noise voltage CL here. Now we could calculate that with all these integrals and so on, no big deal, but that's kind of painful, and we've done it already, and so we just try to remember what it is. Well, first of all, the capacitor is CL, so we got to get a term that is KT on CL. Secondly, our amplifier here also will have a noise factor. Maybe it is that common source stage from the homework, and so we put an NF, let's say NF2 and NF1, just to make that clear. And then we've also, remember the large example at the end of our noise lecture, right? It looked at the case where when we actually have feedback around the amplifier. Well, during phase 1, of course, the feedback is kind of broken, but during phase 2, the situation is precisely equal to the situation that we had analyzed in that example earlier on in class, right? So I remember what the result was. The result was this KT on CL times a factor that included the fact that we used the cascode and so on. Well, here we don't have a cascode, we have something else, and we just call that NF, and the value is in your homework, right? And then there was 1 over the feedback factor, and this feedback factor is not equal to this, right? This is actually larger than this factor. The feedback factor is equal to CF over CF plus CS plus CP or CGS or so, right? Which again is sort of the point that the noise from the amplifier is amplified by more than the signal, which is amplified by this factor. Too bad. So then, of course, we can rewrite this or sort of factor this out or so, write it nicely. So VON square is equal to KT on CF times CS over CF. This is really the gain, AV, of the closed loop amplifier for the signal, right? Times NF1 plus 1 plus KT on CL. Oh yeah, and now I also just remember that the CL was really the CL effective when we did our big noise example. Right? Now you see how handy it comes in. You do this once and you really write down the result very nicely, and you can reuse it all the time, and you can save a lot of time. Right? You can probably from now on the homeworks are sort of a variable thing. It can take half an hour, or if you reuse results that you've calculated, or it can take 2 days if you have to rederive everything from scratch. So this is L effective, and times 1 over F times NF2. So this also says other interesting things. It says, well, I mean, there are all sorts of consideration for choosing the value of CF. But one of them, of course, is that if we make CF too small, then we get a lot of extra noise. Just like the feedback resistors, right? Noise is one consideration. Of course, there is also stability and the feedback factor F that are affected by choosing CF. We've also said that CF shouldn't really be a lot smaller than CS and CP, right? So now we have yet another consideration when we determine what we are going to use as our feedback network. I say that because I've seen solution where, gee, I mean, CF, bad thing, it sort of adds load and area and so on. Why don't we make it almost zero? Well, no, please not. Huh? Okay. All right, so for now at least, that's pretty much what I wanted to say about this business that, yeah, we can use transconductance amplifiers rather than operation amplifiers. And this switch stuff, it's a little bit uncommon and unfamiliar maybe at this point, but there's really nothing fundamental in the way preventing us from using that. With that, I now focus back on just the amplifier part. And normally we are going to just use our amplifier again in sort of the phase 2 mode. And we're going to use the big resistor to bias things and just figure out how it works there, right? And then later, when we build entire systems, we put together again with the switches. Okay, so the next topic that is very important is fully differential circuits. Okay, well, why is differential such a good deal? Well, because if we had some error coupling into a signal wires, then of course that would be amplified and would appear at the output of the amplifier as an error. And so one common sort of case is, suppose this was actually the input of our A to D converter or whatnot, and it comes into the chip through bond wires. Well, somewhere else on the chip there is also power supply, and perhaps it's actually a digital power supply. And we know that inverters are really horrible things, right? They kind of sit there, and then they short circuit the power supply, and then they sit around again. But the short circuiting the power supply basically means that there is a huge spike of current rushing in, and then things get nice and quiet again, and then they short circuit the supply again. Right? It's really awful if you think about it. But the digital folks, they rule, right? So they do that, and well, this thing here kind of looks like a transformer, and so it is one. So this large DIDT produces a voltage spike appearing across this wire here. And heck, that just goes into a sensitive A to D converter or whatnot, and it's not going to be very good. But if we have a fully differential circuit, well, if they sort of are arranged strategically beneficially, then approximately the same spike appears in both wires. And if the amplifier now only looks at the difference of these, then that signal is rejected. Right? Well, the same thing also applies at the output. And so because of that, we're going to use amplifiers that have both differential input and also differential output. Now, if we think about noise, that also is an advantage because the noise of this amplifier and the amplifier that had only one single output is about the same. Most of the noise comes from the diff pair, from the input transistors anyways. I again refer you to the homework, problem 1. Okay? And consequently, adding the extra output adds no or marginally additional noise, right? So the noise is about the same. But let's look at the signal. Well, the signal is going to be bound between VDD and VSS, right? At best, probably a little bit less than that. Well, this terminal can go all the way up to VDD, and this terminal goes all the way down to VSS. And let's suppose we had a 3-volt supply. Then the voltage across here is 3 volts, right? Well, now we can do the opposite. We can pull this guy all the way down to VSS and this one all the way down up to VDD. And then the voltage across here is 3 volts also, but minus 3 volts now. So the entire output voltage swing of this circuit now is only 6 volts or 2 VDD. Okay? Well, we just doubled the signal power and we didn't do much to the noise. So we ought to win 3 dB. Right? So the fully differential amplifier has a noise advantage on top of everything. Of course, usually we don't quite get 2 VDD, but with the single-ended we also don't get quite VDD. So that's all works out. Okay, now there are a few practical things with fully differential amplifiers. Both the input, we really now have 2 inputs. We have an input VI plus, and we also have an input VI minus. Most of the time, we really couldn't care less about these inputs. What we also have is an input common mode voltage, VIC, that is equal to the mean of VI plus and VI minus. Okay? That's this common mode that, let's say, comes from that voltage spike because of the misbehaved inverters. And so sometimes we want to know about this just to be sure that it is suppressed appropriately. There is also VID, and that is the differential between these two voltages. So that would be VI plus minus VI minus. And again, that would have then this twice range to VDD or whatever the output range was. So most of the time, what we want are really these quantities, because this is our signal and this is our garbage. And we want, of course, to separate the two, and we want to know how much signal we get and how much garbage we get, and hopefully we get a whole lot more signal, right? But when we run SPICE, then these are the quantities that really come out of our simulator. So what we really need is a translator between what comes out of SPICE and what we really care about. There are lots of ways to do that. Most of them are very clumsy and very unfortunate, and some of them are very elegant. And so the obvious and clumsy and not very good thing would be to use some controlled sources or so in SPICE that calculate this. Right? Of course, we can add voltages and divide by 2 and so on. No big deal. The problem with that solution is that first of all, it takes all sorts of circuits, but more importantly, impedances really don't get translated properly anymore. If we want to know the differential input or output impedance of the amplifier, well, if we produce the differential output voltage using ideal sources, the output impedance looking at the other end of the generated VD is now going to be the output impedance of the ideal sources, presumably 0, right? And it's got nothing to do with our amplifier. So a much better solution is to use what's called a balun. Now, baluns, basically a common, or if you can use a little more zoom, please. Or transformers that perform just, that are arranged in such a format that they just precisely perform this translation with, they have positive and negative input voltage, and then the output is the common mode and differential mode signal. And in practice, of course, building a balun is kind of a pain in the neck, because how do you get these transformers, and the transformers are not going to work at low frequency, and on, right? Not ideal, and so on. But heck, I mean, this is only for SPICE again. In SPICE, we have perfect transformers, and they work all the way down to DC, and they're perfectly linear, and so on. So hey, why not make our life easy? If we are investigating a circuit with SPICE, use it, right? So I suggest, much like the references that we talked about earlier, hack that into SPICE, make sure that it's actually working, put a sub-circuit statement around it, and put it into your library that you're going to use from now on. Probably this is one of these things that probably is still going to be useful 20 years from now. Okay. There were several other things that that sort of come into play when we talk about fully differential amplifier. So fully differential amplifier means an amplifier that doesn't just have a differential input, but also a differential output. One of them is this issue of common mode feedback. I mentioned that only at this point here because you may have heard about it and may get confused. I'm not going to really talk about it in detail for quite some time. But what's the problem? Well, the problem is really that in an amplifier like this, when we put feedback around it, and presumably like this, then if you look at it, this feedback really gives only sets only the differential mode. And of course, we could have, let's say here, a 1 millivolt input, and let's say this is the ratio of these capacitors are fixed such that the output is going to be 2 millivolts. Well, but this feedback network says nothing about whether this is 1 volt and this is 1.002 volts, or this is 2 volts and then this one would be 2.002 volts, or, and that of course is the kicker, this could be 10 volts, and well, the other one cannot be even higher than 10 volts. Right? It could be stuck at the supply. So in practice, these fully differential amplifiers, they need an additional circuit that's referred to as common mode feedback circuit that fixes the mean or the common mode voltage at the output of the amplifier to something reasonable, usually about mid-supply. Right? Now, for a while at least, we're just going to design amplifiers. They're fully differential. We're not really going to worry about this common mode feedback. We sort of put in some ideal circuit that makes our SPICE simulations work out right. Later, we're going to talk about how we actually implement this. It's going to be another opportunity for switches and capacitors. Okay, now a little bit less zoom again. Thank you. So the next thing, and that has nothing to do particularly with fully differential amplifiers, but in general with amplifiers, is this business of common mode rejection ratio and power supply rejection ratio. So these short circuits, or these shorthands here, just power supply rejection ratio and this common mode rejection ratio. So what does it mean? Well, see, if we build an amplifier, we know what the input is and we know what the output is, and we want that we have gain from the input to the output. But really, every circuit has lots of inputs. For example, every circuit has a power supply. Well, that's an input to the circuit, right? And the variations of the power supply, and by now we know that, well, they're just a matter of life, or at least life for a circuit designer. Variations on the power supply, they shouldn't cause variations of the output of our circuit or our amplifier in particular, right? Well, in practice, you probably cannot completely avoid that. But at least, let's put it that way. If you build an amplifier, that amplifier should provide a lot of gain for the signal and very little, ideally zero gain, for the power supply. And that thing is called the power supply rejection ratio. So, for example, we have the gain A differential mode, so that would be equal to VOD over VID. And of course, that we would like to be infinite. Right? Then we also have the gain A VDD, that is the gain VO differential divided by VDD. Actually, how do you measure this thing? Just exactly the same way as you measure the differential volt gain of the amplifier, except that your source, your stimulus, is not hooked to the input of the amplifier, but actually hooked on the supply. There is nothing wrong with doing an AC analysis where the supply is biased up at DC-wise 3 volts, and superimposed on it is this 1 volt AC stimulus. And then you look at the output voltage, and there you find what is AVDD. And even if you measure it, then that's what you do. You get your power supply, set it to 3 volts, and then you get a function generator, put probably a sine wave on top of it, right? Put it in series with your power supply, hook that whole thing, and then you don't make it probably a volt, right? The ripple, the AC. But hook that thing to the input, to the supply of your chip, and you measure what comes out at the output. Right? And then you change the frequency and the amplitude and so on, you see how much it rejects that thing, or not, perhaps. Right? So VDD, it's an input, right? We prefer it wasn't, but right, so ideally this gain would be 0. And so now we can define the power supply rejection ratio for VDD in this particular case, and that's then equal to, they're always defined with absolute values, a differential mode over a VDD, and because this one's supposed to be infinite and this one's supposed to be 0, this thing is supposed to be infinite. So this is sort of a figure of merit. How much better is this at amplifying my signal than it is at amplifying my power supply noise. And typically, it's a function of frequency, and we've seen that already in the context of references, where the power supply, of course, is also an undesired input. Usually it's going to look something like this. And if you're good, then this may be 60 to 120 dB here. And then it rolls at some point, it rolls off, and it's not so good anymore. Differential circuits help a lot here also, because we'll see that better when we design them. But really, the power supply is hooked up to through presumably a current source or whatnot, really to the output, both the positive and negative output of the amplifier, and consequently affecting both of them about the same if they are carefully laid out and really symmetrical. Consequently, to first order, the power supply rejection ratio of a fully differential amplifier indeed should be about infinite, very large. When you build a single-ended amplifier, that's much harder, because there really VDD is changing, and you have some capacitive coupling through your current source that otherwise, of course, shouldn't couple the voltage through, and so you get much poorer power supply rejection ratio. Similar thing for the common mode rejection ratio. So here there are really two gains. There is the common mode gain, ACM, that's V out common mode over VI common mode, and I guess that should be 0. Usually this is small. Why? Well, because this common mode feedback circuit that we've sort of not talked about. This circuit actually sets this value to a constant voltage and consequently effectively breaks the feed forward from VIC to VO. Also, it's not really, this figure is not that interesting because hopefully the next amplifier that we stick this signal into has a good common mode rejection ratio. In other words, it doesn't look at this signal, it looks at VOD, and then a little ripple on this really ought not to hurt things too much. So then the other one that is very important is the ACDM. That's the output differential voltage over the input common mode voltage. Now this really we want definitely to be small, right? Because we really don't want to generate an output differential. The minute we generate an output differential voltage from our undesired input, the game's over, right? Because that now mixes with the signal. We cannot separate them ever again. And so the common mode rejection ratio, the definition of common mode rejection ratio that I prefer is a differential mode over a CDM. And that should also be infinite. Some books, they define the common mode rejection ratio as ADM over ACM, but it really doesn't have a whole lot of, it doesn't mean a whole lot for circuit designer. Okay, so these are very simple concepts. We just, I guess I made an example here just to, this is a little bit trivial, just to make that point again. So first of all, in this example here, I have a single-ended amplifier, and then I also have a differential amplifier. And so now my input signal is a differential signal, and because the input of the amplifier is, of course, two individual VI plus and VI minus inputs, I use a balun to do the translation. So once you've made that sub-circuit, it's really very, very convenient, right? You don't mind anymore having to deal with all these different signals. You just translate very easily. And then again, the same thing at the output. The output, of course, is again VO plus and VO minus. What I'm really interested is VOD, and the balun is the solution here. Okay. And then I'm doing precisely, I use this to figure out the power supply rejection ratio. I do this. I do this exactly the way I said we should do that. So I said actually my VSS is equal to minus 1.5 volt DC and 1 volt AC. Okay, that's what's written there. And then VDD, of course, that's a DC. Well, I don't even use it here, but that would be another 1.5 volts. So plus minus 1.5 volts. It's my supply. And the VSS has this ripple on top that I model with an AC source here. Okay. Then I also put just a 10 femtofarad capacitance from the input of this amplifier to ground. A little bit of wiring or so. I mean, 10 femtofarads, you get that quickly, right? Not unreasonable. I also put the 10 femtofarads at the input of this amplifier, but I put it on both strands, arguing that I really do a very symmetric layout, and consequently I get the same parasitics on both nodes. Okay. And then I run a power supply rejection ratio analysis. So I calculate this transfer function, get the ratio to get the power supply rejection ratio, and then lo and behold, what is it here? Yeah, the power supply rejection ratio of the differential amplifiers on the order of 300 dB. Would we actually get 300 dB? Well, of course not. I mean, this bound, actually, why is it not infinite? This bound, this is just an artifact of the fact of using 64-bit floating point number. So actually you can diagnose what arithmetic your computer is using with this circuit. Okay, but in practice, right? I mean, the matching may be 1%, 10%, 1%, 0.1% or so. Then it should really be better by a factor of 100 or a factor of 1,000 compared to the single-ended case, which gives here this is 40 dB for the single-ended. Okay? So we can get very significant enhancement. Right? If we match to 0.1%, which is not unthinkable, then we really would have 100 dB for the fully differential amplifier and just 40 dB for the single-ended amplifier. And of course, the difference could be that one is acceptable and the other one's not. Okay, so now having made all these arguments how important it is to have a fully differential input and a fully differential output, we go right back and look at the completely single-ended common source stage. The reason for doing that is that every amplifier, be it differential, two-stage, whatnot, so it's really a transconductor and a load. Every OTA, that is. Right? And of course, the simplest circuit to implement that and therefore to analyze is the common source stage. So we go again through the common source stage and we go and look at all the performance metrics. It's very simple. We can put together our test circuits to investigate this thing, much simpler than having a monstrous amplifier where always something breaks and gets in the way. And then afterwards, when you have the big one, well, we already know how to evaluate it. Okay. So here I actually list some of the characteristics that we're interested in. We of course want to know the gain, and we want to know the output range that our amplifier can achieve. We want to know the bandwidth, how fast this thing can go. We want to know the noise. Later we're going to add more things to this. We're going to add also, well, what is the input impedance? What is the output impedance? What is the settling time or so of this amplifier? There are other considerations, but let's focus on these right now. The amplifier is very simple. This is the amplifier here. This is the actual amp, and the whole rest is just, this is the load, of course. Very important that we always include a realistic load when we characterize an OTA, because the results depend a lot on the load, right? And so if we leave that away, we kind of have to start all over when we finally figure out what it is. Okay, so this thing here sets up the bias, a simply diode-connected transistor. Here I put in a huge capacitor. Why? Well, in order to get rid of noise, right? Because I really want to know what this thing does, not what my biasing network does. And a fixed source. And then, again, there is this old business of, heck, I need to bias this somewhere in the high gain region, right? So I cannot bias this at 0 volts. The transistor would be turned off. But what is the right voltage? Well, I figured that out with a similar amplifier that I just provide feedback between the input and the output. And so it produces the correct VGS here, so that the transistor of this size runs precisely the current that I stick into it, and because the current here and here is the same, the VGS is also ought to be the same. Just yet another way on how to do that. There are 100 ways to do that. You never built this, but in SPICE it's convenient to have something. You need something like it, and I find that more practical than writing down DC bias levels to 5 digits and so on. Okay, so then when characterizing this thing, I always start with a DC analysis. And it's kind of silly, but you know, most of the time I find actually that it doesn't work the first time around, because I always make a mistake. But then at least I don't waste a lot of time finding my mistake. Right? So this is my this is the characteristic. Not too surprising. This is an inverting stage, and it's inverting about bias point of 0 volts. Right? I do everything with respect to the nominal VGS that comes out of this stage. Right? So that's why I call this 0 volts. This is really the VGS that I need to run that current that my other circuit calculates. I also plot the overdrive voltages, or the V stars if you want, right? And I do that also because, heck, I designed this amplifier so that I get certain V stars, and I want to be sure that at least at the bias level, my V stars are approximately correct, right? Otherwise, again, that hints I've made an error in my SPICE. Very, very tedious, but very useful, and a lot less tedious than finding an error in 200 lines of SPICE spaghetti, right? Of course, we see here also that as we move from the bias point, well, V star is a small signal quantity. Of course, it's going to change, right? Okay. And then the next thing is, that's still DC. Actually, I can use the same analysis, just on my post-processor differently. I can calculate the gain. So this one here is AV. That's dV out, dVi. And then this one here is all wrong. Why is it wrong? Well, we've seen that on our earlier, when we talked about this earlier. Really, what I need to do is I need to really use a correct biasing point. And now I've done that for the input, but for the output, I also should have subtracted the voltage, this voltage here that I'm getting when my input is here. But actually here they are identical, right? Because I diode connected it. So I should have also subtracted whatever it is from the output voltage. I didn't do that, and then therefore I got this wrong result. So if I had done it correctly, it would have looked something like this. Right. The correct AV0 would be something like this. We'll see other examples where it's correct later. I just didn't have the time to update my slide. Maybe you can do that when you run your, I don't know, I think I'm not asking for any SPICE in this homework. Make it really easy, but you're always free to play with this, of course. Okay, then the frequency response. We evaluate that. Nothing particularly profound in here, with the exception, I want to again alert you to how we analyze this thing. Right? Frequency response, the unity gain bandwidth, or the gain bandwidth product of an amplifier that has reasonably high gain, is really determined by the transconductance and the load capacitance, not by or out. Why? Well, because at low frequency, all the current runs into or out, and we get a gain of, let's say, 100 or so, right? But at high frequency, ultimately that gain goes to 0. Well, why is it? Well, because the current increased, the transconductor still delivers the same current, but the impedance here decreased by a factor of 100. So in other words, now one port of the current goes in here, and 99 ports of the current go into the capacitor. Well, the big waste of time then at this high frequency to include or out in the calculations. Right? So that's why you will very often see me just write down GM over CL, and that's the unity gain bandwidth of the amplifier. Okay, so then phase margin and so on we can evaluate of this, of course, and we will see a first order response, just a single pole. Now, well, let's talk about this next time. Let's stop here.